Welcome. Today, we are diving deep into optimizing network topologies for NVIDIA-powered environments. We'll explore how to architect for the massive scale and unique demands of AI workloads. Let's start by understanding why we're here. Traditional data centers deal with thousands of small flows, easily balanced by simple hashing. AI is different. It generates massive elephant flows that can saturate links instantly. If you use standard routing like ECMP, you'll get collisions, leading to high tail latency, the enemy of training performance. To optimize for NVIDIA environments, we must shift our focus to maximizing effective bandwidth and eliminating packet loss through specialized topology designs. Look at this flow. On the left, we see AI workloads generating massive data streams. If we rely on standard ECMP hashing, multiple flows might try to squeeze through the same link, creating collisions and packet loss. This results in high tail latency, slowing down the entire cluster. However, with optimized routing, which we will discuss shortly, we distribute traffic efficiently, ensuring high bandwidth and faster job completion. Ideally, we want to stay on the green path. The bedrock of a scalable AI network is the fat tree topology. Unlike traditional three-tier designs, this is non-blocking, meaning every node can communicate at full line rate simultaneously. We use a spine leaf model here. Every leaf switch connects to every spine switch. This guarantees that traffic between any two servers only ever hops to a spine and back down predictable, low latency. It also provides massive redundancy. If one spine fails, traffic simply rebalances to the others. Here is a classic fat tree. Notice how every green leaf switch connects to every blue spine switch. There are no links between spines or between leaves. This creates a predictable two-hop path for any server-to-server communication. If spine 1 goes offline, leaves 1 through 4 still have full connectivity via spines 2, 3, and 4. This mesh ensures that we maintain high bandwidth availability even during maintenance or failure events. Now, let's specialize. For NVIDIA DGX clusters, we use a rail-optimized topology. Deep learning jobs often use an operation called all-reduce, where GPUs need to exchange data with their peers on other nodes. In a rail-optimized design, we connect the first HCA of every server to the same switch, the second HCA to a second switch, and so on. This creates parallel rails of traffic. It minimizes congestion by keeping synchronization traffic on dedicated, physically isolated paths. This diagram illustrates the rail-optimized concept. Look at rail 1 in pink. GPU 0 from node A and GPU 0 from node B both connect to leaf switch 1. They can communicate directly through that single switch. Meanwhile, GPU 1 on both nodes connect to leaf switch 2. This effectively creates parallel networks, ensuring that heavy traffic from one set of GPUs doesn't block the others. This is critical for scaling training performance across hundreds of nodes. If you are using InfiniBand, specifically NVIDIA Quantum 2, you have powerful tools at your disposal. The most significant is SHARP. In traditional networks, data is sent between servers multiple times to perform calculations. With SHARP, the switches themselves perform the data aggregation and reduction. We also enable adaptive routing, where the switch ASIC evaluates egress queue depths and reroutes packets on the fly to avoid congestion, ensuring optimal link utilization. Here we see SHARP in action. Node 1 and Node 2 send their data values to the quantum switch. Instead of passing both packets up to the root or to each other, the switch calculates the sum or other operation right there in the hardware. It sends only the aggregated result up or back down. This drastically reduces the traffic traversing the fabric and frees up the GPU compute cycles for other tasks. For Ethernet environments, we use the Spectrum-X platform to overcome traditional limitations. Standard Ethernet uses static hashing, which causes collisions. Spectrum-X introduces ROSI adaptive routing. The Spectrum 4 switch sprays packets across all available paths to maximize throughput. Crucially, the Bluefield 3 Super NIC at the destination handles the out-of-order packet arrival, reassembling them perfectly before presenting them to the application. This brings InfiniBand-like performance to Ethernet. Follow the sequence. The source DPU sends a flow. The Spectrum 4 switch doesn't just pick one path. It sprays packets 1, 2, and 3 across paths A, B, and C based on real-time load. Notice they arrive at the destination Super NIC out of order 1, then 3, then 2. The Super NIC's hardware resequences them into 1, 2, 3 efficiently, so the application sees a perfect stream. This utilizes 95% of fabric bandwidth compared to tilt 60% with static routing. In a cloud or multi-tenant AI factory, you don't want one user's heavy traffic to kill another user's training run. This is the noisy neighbor problem. NVIDIA Super NICs solved this by enforcing performance isolation. They don't just send data, they participate in global congestion control. Using telemetry from the switches, the Super NIC meters its own data injection rate. It ensures that a bursty workload doesn't overwhelm the fabric buffers, protecting the performance integrity of all tenants. Here we see workload A generating a high load. Instead of flooding the switch buffer immediately, Super NICA intercepts this. It meters the injection rate based on real-time telemetry. This controlled flow enters the switch alongside workload B. Because Super NICA prevented buffer saturation, workload B is not victimized. Both workloads proceed with predictable performance. Without this metering, the switch buffer would fill and workload B would suffer packet drops. Before traffic even hits the NICs, we optimize inside the rack. This is scale-up. NVIDIA, ASNV-Link, and NV-Switch technologies allow GPUs to talk to each other at massive speeds -1.8 terabytes per second. With the GB200 NVL72 architecture, we connect 72 GPUs into a single NV-Link domain. They act as one giant GPU. This is crucial because it keeps the heaviest communication traffic, like tensor parallelism, entirely off the Ethernet or InfiniBand network, reserving that bandwidth for inter-rack scale-out communication. This diagram separates the two traffic domains. Inside the rack, left, 72 GPUs connect via NV switch trays using NV-Link. This supports the massive bandwidth needed for model parallelism. Only the traffic that needs to leave the rack, scale-out traffic, traverses to the InfiniBand or Ethernet fabric on the right. By handling the heavy lifting inside the rack with NV-Link, we optimize the overall topology performance. Optimization isn't a one-time event, it's a life cycle. To maintain these topologies, we use advanced telemetry. What just happened? WJH gives US streaming data on exactly why and where packets are dropped. It's not just a counter, it's root cause analysis. NVIDIA NetQ allows us to validate our configuration against a digital twin to prevent misconfigurations. UFM, Unified Fabric Manager, monitors InfiniBand health, identifying degraded links so we can repair them before they impact a training job. True optimization requires constant visibility. This is the operational loop. We start at monitor. When WJH detects a packet drop or NetQ sees a config drift, we move to detect anomaly. We analyze the specific packet header info provided by WJH to pinpoint the issue, e.g. a bad cable or ACL drop. We remediate the issue perhaps by draining a node. We validate the fix against our digital twin design and then return to monitoring. This cycle ensures our optimized topology stays optimized.